So welcome everyone. My name is Maciej Cytowski. I'm the head of scientific services here at Pawsey Supercomputing Research Centre. Today I'll give you an introduction to Pawsey. That will be organized in mainly two parts. I'll start with just an intro to Pawsey, tell you who we are, what we do, and then in the second part, I'll just give you a bit more information about why you should be interested and when you should be interested in using our resources for your research or for your study or for any other projects that you might have, and give you a bit more details on how to access Pawsey as well. Okay, next slide. So who we are. So what we very often say is that the most precious asset of Pawsey is Pawsey people, and here are the around 50 Pawsey staff members who represent various disciplines. They also represent various expertise. Probably a half of Pawsey team is actually looking at supporting the supercomputing and visualization and data infrastructure from the system administrator perspective, and from the deployment, and also from basically running the infrastructure that we have here at Pawsey. They have multi-year experience in supporting and working with various supercomputing infrastructure, as well as data storage infrastructure and visualization infrastructure. But we also have a part of Pawsey, so the services part, which is working closely with researchers to help them to use the infrastructure, and also to help them to scale their science on amazing big supercomputers. And within that team, we have people who usually have so staff members, colleagues who have usually research backgrounds coming from various disciplines of scientific computing, most of them having PhDs in various areas, to make sure that when we speak and talk to our researchers, we can find similar language and understand your issues, your problems, and then also show you how you can actually leverage the infrastructure we have to solve very complex problems. We are also very proud and happy to collaborate with our partners. So that's all universities and all scientific institutions, as well as government institutions in Australia, but especially CSIRO and all the partner institutions. And I'll mention later who they are. We are also very proud to be a very diverse team. Within the around 50 people working at Pawsey, we are representing around 15 countries altogether. But we also think that pushing that diversity and inclusion even further is extremely important part of what we do. We do collaborate with not only national but international organizations to make sure that this is addressed on multiple levels. So not only from the supercomputing center perspective, but also on the levels of education, so lower, higher education, as well as training and making sure that every opportunities that we create as Pawsey to upskill researchers, students, high school students, and so on is addressed in a way that it's diverse and inclusive. We have identified, and we are not alone in that. We have identified that this is something that will allow our business to perform better, but also create a better workplace for everyone. Pawsey is headquartered in Perth, WA, Wadjuk country. So this is the photo that you can see is a bird eye view of the Pawsey center building. All the systems that we operate are located in that particular building. There is a nice virtual tour that you can take. Unfortunately, normally we would probably meet in this building. We also have a very nice exhibition area and a area to organize such meetings. But for now, today we'll offer you the virtual tour, which you can just join by going to tour.pawsey.org.au. Hopefully a year from now, when all the new infrastructure that I will be covering a little bit during today's talk will be already installed and available at Pawsey. You will be also able to join in-person tour, which we happen to organize. I mean, we used to organize before COVID pandemic. Also, community tours were something that we are organizing very often at Pawsey. But yeah, please have a look at Pawsey from the virtual perspective by going to that site. Okay, what do we do? So, and why do we exist? So we are here to support Australian researchers, and Pawsey has been seen as a tier 1 center, critical Australian compute, data, visualization, as well as cloud infrastructure for research. We can also be seen as and it's quite a unique thing about Pawsey, can be seen as a tier 0 site, which in respect to the support of a critical infrastructure that is being built here in WA. And that's the square kilometer array scientific instrument that will be built 800 kilometers north of Perth and Wajari Amati country. Currently, Pawsey is supporting 2 precursor projects of SKA, that's NWA and ASCAP. It's making sure that researchers building telescopes there in the desert can actually transmit and process the data that are coming from those instruments on our systems, and then store also scientific results and make them available for other researchers to find answers to some biggest challenges of our today work. Pawsey is actually a joint venture, and unincorporated joint venture of 4 Western Australia universities. That's Curtin University, ECU, Murdoch, and University of Western Australia, as well as CSIRO, and with CSIRO being our lead agent. However, Pawsey receives funding from government, federal government through MCRIS, so the National Research Infrastructure for Australia, as well as from state governments. About 2-3 years ago, we have received a capital refresh funding, 70 million Australian dollars capital refresh funding from Australian government to refresh all our infrastructure. And I will be, mentioning that a couple of times during today's talk because it's quite important for future of Australian research in general, but also might be quite interesting for you. I know that we have a lot of intern students joining today's session, so hopefully you will get some information about our new systems that will become available from the beginning of next year. And then with an extreme upgrade in the middle of the year, this will be really exciting times for everyone. But I think there will be also a lot of opportunities for students to get involved in what we will be doing, because all the infrastructures will be super exciting, and not only from the perspective of its scale, but also from the perspective of the new hardware that we'll be installing in the CPUs and GPUs and a couple of other things. So we will need help with making sure that we can, find maybe new algorithms or other things for that infrastructure. But I'll go back to that later. I'm probably going a little bit too deep into that particular topic now. Okay, so we are working in a few areas that I already mentioned some of them. Of course, our core area is the supercomputing capacity and power that we provide to Australian researchers, working with them to make sure that they can upscale their models and research to use tools like massively parallel computing or acceleration through GPUs or other devices, as well as making sure that they can make use of some advances and most modern algorithms available in AI or machine learning. We are also working very closely with radio astronomy community, and that's through MWA and SCAP projects, and looking forward to SKA, working very closely with SKA headquarters to define how the center will operate and run in future. We are, as I mentioned, quite a unique organization in that term. We're one of the only HPC centers to ingest real-time telescope data from the telescope located there in the desert. We are also working with quantum computing, which is, we are mentioning it here because it's something that is maybe not like the core business or core services that we are offering to our researchers, but it's a part of like a future technology roadmap for Pawsey. We are trying to also look at the new technology that is being available in the market, and quantum computing, of course, is something that if you look around the world and the number of startup companies that are looking in that particular topic, and also the companies that are developing new devices for quantum computing, this is a significant and very important area. At Pawsey, we are looking at making sure that we are ready to integrate quantum computers with HPC environment. And we are actually working very closely with one of the startup companies, that's Quantum Brilliance from Canberra, to make sure that their devices will be able to talk or be connected with our supercomputers, because it's more or less clear for everyone that quantum computer will require also big classical computers like supercomputers to operate at scale. We are also working closely with researchers to look at such challenges. I mentioned that supercomputing is the core area for Pawsey, but we are also providing a lot of complementary services, and that's cloud computing, data storage, and visualization. We recognize, and that's something that is, across the board. If you look at all the scientific disciplines, we recognize that it's not only compute that is now needed. It's researchers need high performance storage file systems. Also need a lot of of online and offline storage to store the results of the research, and also must have a specific tools available to analyze the amazingly big data sets that they produce on supercomputers. So it's so Pawsey is actually a set of services that we operate to researchers to make sure that you can do all those steps of your science within Pawsey without moving data outside, but just to basically connect with Pawsey remotely and do all those important steps of your research within the center. We are also working, I'll just shortly mention some of our projects in which we are working closer with the research groups. That was an idea that, so PACER stands for Pawsey Center for Extreme Scale Readiness. That the center was, and the idea for funding the center was actually came from the fact that the new system that we will be installing here at Pawsey is very similar in its architecture to the biggest systems that will be available in all over the world. So Cetonix, the new system for Pawsey, is an HPE Cray EX system, which is very, basically it uses the same architecture as Frontier, which will be soon the biggest supercomputer in the US. Probably might be one of the first exascale systems listed in top 500 list, which is like a ranking of the biggest supercomputers. And Lumi, which will be soon the biggest supercomputer in Europe. Pawsey is working closely with others to make sure that we can support science on Cetonix, but also maybe even to scale them up on those other systems. And because of the fact that the architectures of the systems look very similar, this is a unique opportunity. For that reason, we decided to partner with 10 projects that actually are coming from various institutions across Australia. They represent in total 18 institutions, which also show you how collaborative environment that is. And we also have some collaboration with US national labs and industry as well. And Pawsey is co-funding a PhD or postdoctoral positions that are embedded in those groups, working together to make sure that these people can then optimize the codes and workflows for biggest supercomputers. Each of the projects has also their mentors on the Pawsey side working together and defining the needs and defining the all the activities and work plan for on the technical side of things to make sure that those codes and those researchers and their groups are ready to use the new supercomputer. So I think one of the key points here that I wanted to share is that we are trying to be not only to provide you access to our infrastructure, but using this unique asset that Pawsey has. So the support teams, usually with a research background, we are actually trying to be embedded in your research and help you out with to upskill and also to upscale your workflows for new supercomputers. Okay. So the new system that we'll be installing, which is currently partially installed already on the floor of the Pawsey's server rooms, will be called Cetonix. Cetonix is a scientific name for quokka. We decided to choose this extremely happy animal that is local here to WA. As a representation of how happy we are with the infrastructure that we'll be installing here at Pawsey. That's actually the real photo of Cetonix. So you can also see that we are also trying to represent our connection to the land. The artwork that you can see here is a painting from Wajari artist Margaret Whitehurst. I'm also having this the pretty same artwork on my shirt. We are very proud to stay connected to the traditional owners and also to the land through everything that we do at Pawsey. But Cetonix is actually quite an exciting milestone for Australian research in general. Once it will be installed and then fully installed in the mid-2022, it will become the biggest supercomputer in Australia and one of the biggest supercomputing in the region as well. It will have 50 petaflop of performance. I will comment on what it actually means in a second. And yeah, it will become the most powerful research supercomputer. It also comes with a couple of other things. It's not only the supercomputer and the processing power, but also a lot of exciting infrastructure related to storage and visualization, which I will cover later. But we are very proud from the fact that we are able to build and partner with HPE to build this supercomputer for Australian researchers. Just to give you an example and a representation, or actually, just to show you how it actually looks in comparison to our current resources. So the current system that we are operating at Pawsey is called Magnus. It has 1.1 petaflops. Petaflop is a measure of compute performance of the system or compute power of the system. The phase one system, which you've seen on the photo on the previous slide, has 2.7 petaflops. Also, to give you an idea, Magnus is located in 8 huge cabinets. The system that you have seen in on the previous slide has only 2 cabinets and then one cabinet, additional one, which is a cooling distribution unit, CDU. So you can actually see how with time we are able to make, or the hardware vendors and CPU and GPU vendors are able to make those systems more efficient in terms of the space they take, but also in terms of the energy. So the final system, Cetonix Phase 2, which will be installed in the mid-2022, will have 50 petaflops compared to Magnus, but will only use 1.5x more energy. So that gives you also an idea of and answers the question why we need to make sure that those big supercomputers that are built to be available for researchers have to be refreshed and have to be rebuilt every now and then, because it's basically you are able to provide like almost more than 40x power in terms of compute, staying in a very similar energy regime, which is a huge improvement. So what the petaflop is? So petaflop is flop is as I mentioned, a measure of performance. It stands for floating operations per second. So how many basic operations on floating point numbers a supercomputer can perform within a second? And then we have this what does it mean comparison, which basically tells you that if any one of us would be able to solve one such calculation each second, it will take us around 31 million years to solve what Magnus can do within a second, right? And to be honest, I mean, if you then compare it to how those systems are being used, it's actually quite amazing that you might see on Pawsey and systems, you might see researchers that are actually able to use the entire system to run a specific simulation. For instance, a computational fluid dynamics simulation is looking at how future engines will be efficient, for instance, looking at turbulent flows in jet engines. This is why we build such infrastructure, to actually make it available for those researchers that actually need this entire system to run a single simulation or couple of simulations to find important answers to their computational challenges. But use cases of Magnus and other systems there are also other use cases related to accelerating workflows on GPUs and so on, but we'll get to that later. For those that want to know a little bit more about Setonics, very shortly, a couple of slides showing that the system will have around 3,200 AMD Milan CPUs, each with 64 cores. That will be altogether more than 200,000 CPU cores. We will also have AMD next generation Instinct GPUs. That's around 700. We'll have around 768 of those GPUs. And if you are looking at the recent announcements of AMD that were just made, I think 2 weeks ago, for a year or so, we are not able to talk about the GPU that will be installed at Pawsey. But 2 weeks ago, there was a very important announcement from AMD where they actually announced this next generation product, which is called MI200. And if you look at the details of it, the actual GPU that will be installed at Pawsey will be called MI250X, with 128 gigabytes of memory and really amazing compute power that can be delivered for scientific computing. But what is quite important also from the perspective of supercomputing to be able to use all that resource efficiently is the interconnect. So the network that is connecting all those compute devices, CPUs, GPUs, memory, and so on between each other, that can provide the scalability, meaning that you are able, for instance, to run your code twice as fast when you are using 200 or let's say 2000 CPU cores compared to 1000 CPU cores, so that you are able to scale your code and get it accelerated as you use more and more CPU cores or more and more GPU devices. So in that case, our system is based on an HP Cray solution, which is called Slingshot, which delivers from between 200 and 400 gigabytes per second for the CPU nodes, and up to 800 gigabytes per second for GPU nodes. There is also a high-performance scratch file system, which is partially based on SSDs and disks. But yeah, these are just technical details. But I guess the most important part is actually how you'll be able to use it, and how to prepare for using it, and so on, so on. The good information is that we will be the environment and programming environment for that system will be very similar to what we currently support on Pawsey systems, and we'll be also providing support for things like containers, for the AI machine learning packages that you might know. Those will be also supported on the AMD GPUs and so on. So we are currently now very busy at Pawsey to make sure that the transition to the new system will be, will be very smooth for all our researchers. From the architecture point of view, if you look at Pawsey, this is how it will be looking like half a year from now, when Cetonix will be already installed at Pawsey. So we'll have Cetonix, which will be our main supercomputer, but also a couple of other systems. We have a Topaz NVIDIA GPU cluster. We have ASCAP ingest nodes that are, being used to transfer the data from radio astronomy instruments. We have a Gara-Warla system, also a GPU system, which is currently being used by NWA Group to process the data coming from their telescope. But we also have those complementary services that I mentioned that are super important to actually allow you to do many things on the supercomputers now, is the Nimbus Cloud, and also the quite extensive storage system, which actually is composed of two components. A Ceph file system, object storage file system, which will have around 60 petabyte usable, and 70 petabyte tape system, which will be used and available as an offline storage. We are also trying to make sure that whatever we do, and that's I mentioned on the in the case of the comparison between Magnus and Cetonix in terms of how much computational power it can provide, but how much energy it will be using compared to Magnus. We are also looking at all other ways to make sure that we can provide some smarter supercomputing in terms of energy efficiency, green computing, and so on, so on. So the building itself was designed in a way that we have dual skin building. We have around 400 photovoltaic panels installed on the roof, which provide additional electricity to basically save the carbon and reduce the carbon footprint of the compute. The new supercomputer that we have chosen is 100% liquid cooled, which is quite amazing if you look at the infrastructure itself. If you look at the all the components like CPUs, GPUs, memory, and also network interconnect, chips and switches, they all have liquid cooling installed on top of them. So if you actually look at the system, I think we had it on this slide. If you look at the system from on its back, you can see a lot of pipes. You can clearly identify which one are the inlet one and which are the outlet ones. So the blue ones with the cold and liquid, and the red ones with the one that comes back after cooling down all the devices in the system. We are also looking at future possibilities to even improve carbon footprint of compute because it's something that every researcher is looking at the moment. One of the ways, actually, also to probably one of the most important ways to make sure that you can reduce this carbon footprint of your compute is to make sure that your application is well optimized for the resource you are using, and that's where again Pawsey team comes in and with providing benchmarks and also recommendations on what you can do to actually speed up your code so that you use the system more efficiently. We also have a lot of researchers doing research on new energy transition, looking at energy waste, clean energy, hydro, battery energy storage, oil and gas, and so on, so on. From the perspective of how many researchers we support and where they are located, I mean, most of them, of course, are from Australia, so around 3,600 researchers. But we also do allow and actually encourage worldwide collaborations. So there are a lot of researchers that are actually setting up a research projects together with the collaborators from various other countries. So Europe, North America, Asia, New Zealand, and Africa and South America. We also work very closely with international organizations that are listed here on the left-hand side of this slide. Just recently, we also signed an MOU with Lumi. So that's the biggest system that will be installed in Europe that will be available for all European researchers, which happens to have the same architecture as the Pawsey Statonic system. We are hoping that this will bring also new opportunities for all researchers in Australia. So give you a little bit of information of what Pawsey can do for you when you should use Pawsey and start to think of using Pawsey, and how to get started with Pawsey. Okay, I will start by saying that as I mentioned throughout the talk, Pawsey is helping to supporting some of the grandest challenges facing our world. I will share probably an information of where you can find some really cool examples of what our researchers are doing on our infrastructure. But in general, from the researcher's perspective, if you are an Australian researcher or scientist, you can use our resources for free. And then I will later say what it actually means, because there is a specific application process. And always in that case, we also should acknowledge that this is free from researchers' perspective, but we are actually being supported by federal and state government, as well as our partners, to actually build that infrastructure to make it available for you. This is actually a model that works very similar in all other countries around the world. That the supercomputers are being, the big supercomputing national facilities are being funded by the government, so that then researchers can apply and use them for their research to progress national science initiatives. And we are actually very active and supporting various areas of research. So for many years, I mean, actually, when Pawsey was funded, we were funded as an institution that was about to support mainly radio astronomy science related to SKA. But as we grew in our competences, and as we grew with our infrastructure available at Pawsey, we became a national supercomputing facility supporting all the major scientific and computational science domains across the board. So we are now working with health, agriculture, resources, and energy projects, but also many more disciplines or so. So just to give you an idea of what it actually means and when you would decide to use such facilities, we actually identified that there are very similar patterns on how researchers will do their science, right? So usually now you are looking at collecting or using some data for your processing. Then you will have the data connected. It might be data coming from a scientific instrument like a radio telescope. It might be a data collected via some other processes, or maybe just if you are doing, let's say, weather forecasting, that might be the initial conditions or boundary conditions for your model. Then you will look at staging the data, because the data is usually coming from somewhere else. So you will stage the data on near the supercomputer that you will be then using and then processing the data, right? So you will be looking at where you can actually bring your initial data together, right, closer to the supercomputer. Then how you actually do turn your data into science, how do you process it, how you run your simulations, whether they require, multiple cores and threads to be communicating all the time when they are doing the processing, or whether you can do it on a single GPU, maybe. So how from the technical perspective, you will be processing the data. But then very often, and this is something, again, that we see across the board in all the disciplines, because of the vast amount of data that you are processing and the vast amount of data that you are also generating through those simulations, you then have to look for information within that data so the final science products will not be a terabytes or petabytes of data, will be actual statistics, or maybe some images, maybe two-dimensional representation of the data that allows you to see some important information in the data. So again, I mean, visualization or some post-processing of the data, you need to plan how you are planning to do that on the on supercomputers. And then some of the data products will be shared with outside world through publications or through any other ways. But some important data you might still decide to archive, and then again, where do you what do you do with your results when they are finished, and whether you store it at Pawsey, whether you move it to institutional storage. So to understand when you are actually at the level of, okay, now I probably should go and use a supercomputer like Cetonix or other available here and there, you should probably start to think of what it actually takes to process, and how long it will take you to process your data. If your current issue is that your model is running on your, let's say, a laptop or a workstation, and you need to leave it running for nights when you go back home, because it will take a couple of hours to run, and you're leaving your workstation up and running for the entire day to do some calculations, but you don't need any other workstations. That's probably more a cloud compute problem. You would probably try to then go and look for some cloud resources, whether it's in Pawsey or somewhere else, to allocate your compute and to do the compute there, because I mean those systems are being up and ready for your research 24/7. However, the problem will start when you will see that, well, one workstation is not enough. I should have 2, 3, 4, and so on, because of the fact that I cannot feed data in a single workstation. I cannot process the data fast enough, because, for instance, my processing, even on a single workstation, my processing will take, let's say, a year. That's probably a good moment when you will have to start to consider using facilities like Pawsey. And then the next thing, and the next question you will ask, how can I actually make sure that I will be able to use parallelization and basically parallelize my code so that I can use a bigger resource for processing. And that's when you would probably contact Pawsey and have a discussion with us. And I encourage you to do so, because we, as I mentioned, with us, a lot of my colleagues having expertise in various domains, you will be able to actually get some information how we can help you with that. I will speed up a little bit because I think we only have 4 minutes left. But yeah, this is kind of like the idea of those various stages put on, again, on a single slide, showing you that there is some input and display output, but then in between is all of that is something that Pawsey can support you with, and uptake team training and experts and specialists is the resource, and probably the most important resource of Pawsey. We are excited about Cetonix, but without that additional support, that won't be that efficient. Looking at some of the case studies that are represented here at Pawsey, please feel free to jump on our webpage, pawsey.org.au. You will see a case studies, so science showcase, and then case studies link. This is where we are sharing some exciting science that our researchers are producing on systems. And I would quickly jump through some of the examples. We have a very exciting collaboration with UWA. Dr. Janice Noley is actually looking at using machine learning to work on the cardiac data, to understand actually, real time what can happen to a patient based on the data coming from the devices that are connected to patients in the hospitals here in Perth. We also have researchers that are looking at designing better batteries, so new energy sources or more efficient energy sources. but also a lot of bio science, looking at not only human genomes, but also plant genomes, and for instance, making sure that we can improve crop performance, which is quite an important food security topic going forward for every one of us. Okay, so now again, quickly through like a summary of what we can provide in terms of the supercomputing services, experts advice, solution design and consulting in terms of how you can accelerate your code, parallelize your code, optimize your workflows, or for instance, benchmark or profile your applications. In some cases, we will work with groups on code development and optimizations, and that's the Pacer example is a very good one here. The main focus here is on large-scale computing support and research. From the perspective of the Nimbus Research Cloud services, again, we provide expert advice, solution design, and consulting. You can also receive support in creating your virtual machines on the Nimbus Cloud. However, quite important information on the supercomputing services. Once you get access to the supercomputer, you will get also access to multiple tools that we do support, like compilers, applications that are supported on the system. On virtual machines, just like in most of the other cloud providers, you would have power to actually manage the VMs by yourself. However, we also provide you with recommendations and use cases how to use some specific tools on our cloud infrastructure. And the examples here are Kubernetes clusters, Jupyter hubs, Singularity containers, and RStudio. Managed data services provides you with the capability for building, archiving, and sharing research collections. This is first available, of course, for all the researchers running on our supercomputers, but also it is available for other researchers that don't do compute in our center, but want to just create data collections for collaboration later. We have a very good examples of collaboration with WA government, for instance, institutions on that side of things as well. And visualization services. So most of the services and tools that we install, visualization tools, are actually available through a remote visualization service, which means that you can actually log into it in your web browser and select the tool that you want to use to visualize your data and work on the data that is stored at Pawsey. So you don't need to move the data outside Pawsey to visualize what is hidden in the data. We also have a brand new, and that's again related to the capital refresh, a brand new VisLab, which can be seen here on the right-hand side. And we provide also support for in-situ visualization. So basically doing the visualization during the actual supercomputing simulation. So instead of running a simulation, storing data, and then doing post-processing, you can actually do it on fly, which is quite cool. To see how you can actually access our resources, I would encourage you to have a look at the documentation pages we have. A lot of changes actually will be applied to Cetonix. The current for supercomputing, for the core service that we are running for supercomputing, you have to apply through merit allocation schemes, so National Computational Merit Allocation Scheme and CMAS or Pawsey Partner Scheme, if you are a member of Pawsey Partner institutions. But there will be more schemes that will be available for Cetonix in mid-2022 when the system will be at full scale. So please have a look at this, keep an eye on that, because there will be some exciting new opportunities in terms of accessing the systems. For the merit allocation schemes, there is a yearly call that you have to submit a proposal to. The calls are usually published around August, September. Nimbus and managed data and visualization, please have a look at the documentation pages. But those are the services that are available for our supercomputing projects, and also for those that don't do compute. There are some ways, of course, to also apply only for managed storage allocation, or only for Nimbus access, or only for visualization access. All projects are subject to reporting, yearly reporting, or when your project is over. And the last things, we also have a lot of training opportunities, in-person, virtual, hybrids. Yeah, we are getting back to organize also in-person events, hopefully very, very soon. We have run extremely large number of virtual events over the last 2 years. Please have a look at our GitHub page, training page, which allows you to look at all the resources, training resources that we have. Also to filter those resources by core, intermediate, advanced, but also about in the actual topic that they touch. So yeah, please feel free to jump there and have a look. If you have a problem, please use the help desk service that is available for all researchers. And even if you have a question on how to get access to our resources, please submit a ticket and we will respond, or just send an email to help@pawsey.org.au. Documentation pages, I'll probably skip that. And if you are planning to become Pawsey user, also have a look at our conditions of use, which define things like what you need to do when you publish a paper that was basically enabled by accessing our resources is related to some compute that was done at the center. A few links, and I think that's it. Are there any questions? How does Cetonix compare to the supercomputers in Europe? That's a good question. So, so one of the ways and actually this is something that a lot of, centers do, they try to compare the scale of the system to scale of other systems. One of the ways you can do it is to rank your system on something which is called top 500 list. So top 500 list is you basically have to run a single code on your entire system. The code is doing some very basic matrix computations. It's called high performance LINPACK. And basically it runs on all the CPU or GPUs available in the system and produces a single number. Of course, it also says whether the calculations were correct or not, but then it actually produces a single number. And this number is the measured flops of your system. So you have a theoretical compute power of your system, which is basically computed by the number of devices that you have and their theoretical compute power of each CPU and GPU. But then you can actually measure it. And high performance LINPACK is a way of measuring that performance. So when Cetonix will be fully installed and listed on the top 500 list, we are expecting its result to be probably around 40 petaflop of measured performance. Whereas the Lumi system that I have mentioned, once it will be fully installed, will probably represent around 400 petaflops. So this is 10 times more that Pawsey's system will have. So from my perspective, it's very important, and this is what we are trying to do, is to collaborate with other centers. And actually, what we find very, very nice is that they also are very keen to collaborate with us, because there are some things that we have already looked in terms of AMD GPUs preparations for running codes, and that they can benefit from learning from us. So this is a very nice collaboration that we have started some time ago. And also you must know that Lumi is actually, although it will be placed in Finland and run by a supercomputing center called CSC, it is actually a collaboration of all European countries that have gathered within something which is called EuroHPC, as far as I remember. And so Lumi is actually a collaboration of 10 countries with user support teams in each country, making sure that researchers for those countries will be able to use the resource efficiently. Okay, Maciej, early on you mentioned exascale computing. What does that mean? Yeah, so I mentioned petaflop. So I told you what a flop is. I didn't tell you what peta is. So peta is 10 to the power of 15 of flops, right? So 1 with 15 zeros. And it's a kind of like, it's considered to be a milestone in supercomputing to reach another level of computing by adding like those 3 zeros, let's say. So exascale, it's related to actually exaflops of a system, right? So exaflop system will have 10 to the power 18 of flops, and we were expecting actually for such system to be listed on top 500 list this November, so last week actually, but it didn't happen because they were not able to run that benchmark that I have mentioned in time and have the system listed on the top 500 list. However, the rumors say, and those rumors, we have more evidence that actually there are few systems that already broke that barrier of an exaflop, and with 2 of those systems located in China. So it's a kind of like you can say a competition or a collaboration of all the vendors and supercomputing centers to make sure that they can build bigger and bigger systems to support science. Okay, another question is 128 gigabytes local memory per GPU with 4 GPUs per node is a lot of memory. How much RAM does each node have in comparison? Yes, so that's true. One information is that most of the GPU nodes will actually have only 256 gigs of local RAM, which from that perspective might seem to be not enough to work with all the memory available within GPUs. But there are 2 informations that are interesting. So first, some of the nodes will actually have an increased memory, I think up to 512 on the RAM side. And the other information is that those new GPUs, so the MI250X GPUs, they integrate with CPU and CPU memory in a totally different way than all the other GPUs in the past. So those GPUs will integrate with a special version of an AMD Milan CPU to create a cache coherent environment within a node. So basically, what it means that in general, but we will see, of course, how that will be supported from the programming languages perspective, but we should be able to create a single memory area which can be then addressed by codes or kernels running both on CPU and GPU. We'll see how that will work in practice. Maybe we will stick to a classical model of offloading something to a GPU, but this particular feature, it was also something that we are looking at very closely when we are making decisions about the system, because we think that this might be the future of supercomputing. Pawsey, and what you might have seen in the couple of announcements just recently, is also now involved in something which is called OpenMP ARB. That's the OpenMP Architecture Review Board. This is a body that actually defines the standard of a programming language, which is called OpenMP. And OpenMP used to be, and is available from, I think, 1997 for researchers to run parallel codes on supercomputers. Previously, mostly looking at CPU parallelization within a node, so multi-threading, multi-processing. Currently, it also allows you to run kernels on GPUs, to offload codes on GPUs. We are now included in the architecture review board to make sure that we will be also able to shape this programming model going forward. So
They're coming in fast and furious now, Maciej.
Yes. Okay, let me take maybe the last question. So we have seen a 40-fold growth in performance over the time period between Magnus and Photonics phase 2. Can we expect to see another 40-fold increase in performance over the same time? Well, this is a very good question. The question that is super related, you know, to fund, to how the supercomputing infrastructure and centers are being funded in Australia. But yeah, I think looking at what is already available and will be available very soon in the US, so the Frontier system, which will be an exaflop system, and looking at Lumi installation, I think we can assume that this will happen. We cannot probably state that this will happen, like, you know, indefinitely. If you look at the laws that are actually driving supercomputing and, you know, defining how many transistors we can put on a single die of a CPU, of a GPU, or a GPU, we cannot state that this kind of increase will be available for us. If you look at, you know, the biggest supercomputers, you for sure cannot state that. But for Pawsey, I think this will be something which will be available, because as I said, if you look at the performance of those biggest supercomputers that will be available in a year or so, we can think of maybe one day running a similar system here at Pawsey. The question is probably what will happen with Cetonix being substantially bigger than what we've had available in the previous years. Well, yes, we will work with the researchers. For some of the researchers, it will mean that they will be able to run their models on a totally different scale. I hope, and we are working with researchers very closely to make sure that this will happen, because those systems are being installed and they have more capacity to make sure that researchers can take their science to another level. So this will for sure happen. So we'll probably see that the projects that are currently asking for, let's say, 10 million core hours per year will be maybe asking for 50 million core hours or 100 million core hours. That is also possible in 2023. We are not putting a limit, an upper limit of what you can ask for. There is a lower limit because we want to separate, let's say, cloud computing from supercomputing. So you need to be at a certain scale to actually access supercomputing resources. For Cetonix full-scale phase 2, this system will include a lot of new GPUs that will be not only new for researchers, but also for us. I mean, we have been preparing for supporting those devices for about 2 years now. And we are quite confident that we'll be able to do that for many researchers. But, you know, it will probably take time. The transition will take time. So for the GPU partition of Cetonix next year, we will be actually offering an early adopters or early science scheme. So they won't be available from the start through the merit allocation calls, but there will be an early adopters period, probably of a couple of months, where researchers will be able to transition their workflows to that. And this is by any means, I mean, the GPU partition of Cetonix will bring the most of the computational power of the system. So this is like, we recognize this as like a super important part of the entire migration from Magnus to Cetonix, to make sure that this GPU migration is done right. The CPU migration will be probably slightly easier and smoother. Yeah. Okay.
Thank you, Maciej. There is a question about the SKA when it's fully developed regarding hardware. Will it have a dedicated supercomputing resources, or will the processing be integrated with other resources?
Yes.
What type of hardware?
Yeah, okay. So SKA is an international organization, actually with the headquarters in UK. The instrument that will be installed here in Western Australia is not the only one. There is another node which will be installed in South Africa as well. It's an international. There are multiple countries participating in that project as well. So it's an international effort. Whatever we will be producing here in Western Australia will be not only processed here in Western Australia, but also will be used by researchers from all around the world. So part of the SKA effort is also make sure that we are actually able to share the data efficiently between various sites. Now, with the future of the compute support for SKA, Pawsey is collaborating very closely with the SKA office to make sure that this is this is implemented in a proper way, to make sure that we have good estimations of what should be the compute power of the system that will be installed in this in Western Australia. But part of the work is actually making sure that we can also support it from the perspective of tools. And I think this is more because we will be able, that's for sure, we will be able to build compute systems for processing of data, for sure. But then the question is how you can process the data efficiently of that. For instance, if that will be a GPU-based system, you need to prepare your codes and transition your current processing pipelines to that infrastructure. I think for me, especially, and for my team, the most exciting part of this whole SKA effort is looking at this software challenges of processing the data.
Thank you, Maciej. And we might leave it there. We have a few more additional questions, but we will get to those in the Q&A document. Again, thank you, Maciej, for the presentation. Very interesting, as always. And thank you, everyone, for your questions and for your attendance. With that, we will call it a day. Thanks again, and have a great day.
Thank you all. Have a great day.